Arc length. This is something you may have seen in other contexts, in other forms. Here we're going to look at it in the sort of vector calculus way of looking at it. So what's the length or arc length of a parametric curve? It is, sometimes people write it this way, where you just say it's the integral of c ds, right? What that little s is, this is the arc length parameter, because length starts with s. Um, It doesn't, of course. Uh, it's why we call it S. It's Latin for spatium, which is sort of distance or displacement. So that's for that. That's why arc length is ds. Um, that S. There we go. And then also, how can we then compute that? That's symbols for it. But how do we actually compute that? Well, arc length parameter unpacks to this. Once you parameterize your curve, this is the easiest way to write down the arc length parameter. So this is what is it? It's speed dt, right? It's the velocity vector. We take its magnitude and then um, integrate that with respect to time. Right, so that's the easiest way to unpack the arc length parameter. This is a formula you may have seen, say it was in the two-dimensional case, you may have seen this in Calc 2, right? If you think about what this becomes, right, in a two-dimensional case, what would it look like? Um, you'd have x of t, y of t for r, right? But then it's r prime. So you take each of their derivatives, and then you are taking the magnitude of that. So you do the square root of the sum of the squares. So this, right? Sometimes this formula is in Calc 2. Right? And what's the idea here? The idea here is that, these um, x primes and y primes dt, right? You're essentially getting little change in x and change in y. And then you do the Pythagorean theorem to get the hypotenuse, right? So this little hypotenuse, as you go very small, those line segments connect up to form the smooth curve. And this is that, giving you that little line segment, right? So that's, and then you integrate them all together, all those tiny little line segments to get the length of the curve. So it's a nice construction. Um, What's cool here is this r can be of any dimension, right? And this formula still holds. So you can do, in 3D, you just keep going, right? You then have x prime, y prime, z prime, and you take its magnitude and you get the same formula, but you just have a plus z prime squared. So it's not very different, even if you're in a higher dimension. So this is the arc length integral. What I want to do is I want to look at this in the case of a little bit nastier function. So one where it's not just smooth, but it's piecewise smooth, right? So one that has some cusps to it. So let's look at this in an example. I want to calculate an arc length, but I want to do something a little uglier than a circle or a line this time. So let's look at this curve. So let's say we're given the parametric curve that it's going to be essentially the unit circle, but I'm going to cube both of the coordinates, right? So instead of cosine sine, I'm going to do cosine cubed, sine cubed. And we're still going to take a full lap around the circle, right? So given this curve, find its length. Okay, so what can we do here? We can put the n back. There we go. There we go. So let's just think about what this looks like. So imagine this is essentially, it used to be a unit circle, right? But then I cubed all the x and y coordinates, right? So these points are going to be the same because 1 cubed equals 1, right? So if the x coordinate is 1 and then I cube it, it stays the same. And 0 cubed equals 0. So if the y coordinate is 0, it stays the same. Same thing over here. Like -1 cubed is still -1. So it doesn't move anywhere when you cube it, right? So those 4 points on the axes are going to be exactly the same as they were for the unit circle. Now, what's going to happen for something like, say, in here, right? What are these points? Like this point on the unit circle was root 2 over 2 comma root 2 over 2. So this was something like 0.7 comma 0.7, right? So if you cube that, right, what are you going to get? You're going to get, 0.7 squared would be 0.49. So 0.7 of 0.7, right? Because it's a number less than 1. So when you square it, it comes down. But then we're going to multiply it again. So we're going to 0.49 times another copy of 0.7 to get the cube, right? Um, so then what is that going to be? That's roughly half of 0.7. So it's going to be something like 0.35, right? Um, so both coordinates, when you cube them, they're gonna move towards the origin a little bit, right? You're sort of compressing this figure towards the origin because numbers less than 1, when they get cubed, they keep their sign. The numbers between -1 and 1, right? They keep their sign, but they move closer to 0, right? When you cube a number that's less than 1 in magnitude, so it moves closer to 0. So you're going to kind of squish the circle in on itself. Like this point used to be root 2 over 2, comma root 2 over 2. Now when you cube it, it's going to be more like this point, like 0.35, right? It's going to be closer now to 0.35, comma 0.35, right? So that's going to happen actually to all the points, right? They're all going to kind of get compressed in towards the origin, right? So, but I know they keep the intercepts the same, right? So what is this graph going to look like? It's going to look like this, right? This is basically, you get this really nice star shape for this graph. Okay, so now suppose I want the length of this, right, of this star shape. What can I do here? Well, notice that this has 4 points at which it's not smooth, right? And right, the first 4 points that I drew, right, those are all cusps on this graph. And typically you don't want to do anything involving derivatives or integrals when things aren't differentiable or aren't integrable, right? So that's not to say that it can't work out sometimes by chance, but what's going to be the best strategy here is because of these points where it's not smooth, to find its length, we're just going to find it in the first quadrant, and then we'll multiply it by 4, right? To avoid those ugly points. And just to show you what more specifically, I mean, here I identified the points where it's not smooth just visually, but you can also do it by calculating directly. Right? If we wanted to be more specific about it, what do we have? We'd have r prime. What's r prime for this? It's 3 cosine squared t times negative sine of t, right? And then it's 3 sine squared t times cosine t, right? That's our velocity vector, right? Which means then we can calculate speed from this, right? That's our velocity. So then speed is magnitude of that, right? So it's the sum of squares here, the square root of the sum of squares. So what does this become? It's 9 cosine of the fourth t sine squared t plus 9 sine of the fourth t cosine squared t. And fortunately, these terms have a massive greatest common factor, right? 9 cosine squared sine squared factors out of each of these. And when I do that, the first term, the only thing that remains is a cosine squared. I factored everything else out. And on the second term, the only thing that remains is a sine squared. I factored everything else out. Right. And now take the square root, and what do we get? We get absolute value of 3 cosine t sine t. Right? And then here I have just 1. There we go. Right? So this, you can see those places. See, it's the product of sine and cosine, right? See, so now you can see that the speed vanishes to 0 sometimes, right? So where is speed 0? Right, the curve is not smooth. Where? Well, it's not smooth when the magnitude of the velocity vector goes to 0, right? So when is this formula equal to 0? Well, 3 can't be 0, right? So it's where cosine is 0 or where sine is 0. Which is exactly, at least on our interval from 0 to 2 pi, where it's when t is 0 or pi, right? That's when you get sine being 0, right? When t is pi over 2 or 3 pi over 2, that's when you get cosine being 0, right? So those cosine t and sine t equaling 0 each give us two solutions. And those are the 4 points that we saw in our graph, right? The 4 places where you'd prick your finger if you touch the graph with too much force. So. All right, so that's calculating the places where this curve was not smooth, right? We just took the speed, set it equal to 0. So now if you wanted to do this arc length, like I mentioned, it's just kind of most convenient to not cross those points. And you can almost see it in the formula here, right? This absolute value, right? Something, you can just say, okay, let's calculate the length, right? And say, okay, the length is from t equals 0 to 2 pi of 3 cosine t sine t, right? But this really is absolute value of cosine t sine t, right? Cosine and sine do switch between positive and negative. But like here, see, when I took the square root of the square, right, that can never be negative. That's why I threw the absolute values on, right? If you take a quantity, you square it, it becomes positive. Then you take its square root, it's positive, right? The square root symbol, unless you physically write a minus in front, which we do sometimes. Sometimes we write plus or minus. But if you don't, if you just write the square root, then you mean the positive real root of that expression, right? So this is a place where there are absolute values. So now you have to worry about, oh God, right, on what interval is this absolute value positive? And sorry, the expression inside the absolute value positive versus negative. You have to break up the absolute value according to the sign of what's inside. And you could do that, right? But it's all because of those not smooth points, right? That's why we're getting this toggling sign in our integrand, right? So what's easier is what I mentioned before. Don't do that, right? Just say, you know what? I'm going to integrate this just where it is smooth, right? Just from 0 to pi over 2, right? And now cosine is positive on that interval, sine is positive on that interval. I can ditch the absolute values, right? So this is much easier. And that's what I mentioned up here about multiplying by 4, right? Just do this interval from t equals 0 to t equals pi over 2, and then quadruple it to get the rest of the graph, right? So that's what we're doing here, is just that first quadrant. Okay, then I can integrate this, and this integral is not too bad, right? Combine the constants. This is essentially just a u sub, right? Take u equals sine. So then your du is exactly cosine t dt, right? So this is a super nice u sub. So we can do so this is just the integral of u to u, right? Which is, so I get 12u squared over 2, right? And then this becomes 6. U is sine, so 6 sine squared t. T equals pi over 2 and 0. So 6 times sine squared of pi over 2 minus 6 times sine squared of 0. So the second piece goes to 0, right? Sine of pi over 2 is 1. So I get 6 times 1 minus 6 times 0 is 6. Beautiful. There we go. So there's our arc length of this parametric curve, right? So it's, for being kind of a wonky figure, right? Sine cubed times cosine cubed. It actually has a really nice arc length, right? It's just 6. It comes out to a integer, which is a bit of a surprise, maybe, right? But it comes out really nice. So that's the length of this little star shape. Okay, there we go. So there's the definition of arc length, right? And once again, here I did it in a two-dimensional curve, but it works just the same in 3D or higher. Right, and there's our little example where what did we do? We calculated the speed, right? So remember, this is the speed function right there, right? And we simplified it down to this, right? So again, how did I get the arc length? I just did the integral of speed, right? This right here, this is just magnitude of r prime of t for this curve, right? It's just the simplified down form. So I was using this formula, right? This one right here, that's going to be your go-to when you want the arc length of a parametric curve. So one other comment on this. Could you find the arc length of this using a Cartesian equation? Maybe, but I don't want to. This parametric curve, right? So this is a good, I think, afterthought. Could we have done this in Cartesian? I mean, the answer is 6. How bad could the integral be, right? So maybe try. I don't know. I haven't actually tried, but it looks pretty bad. So here's, what would you have? You'd have x and y, right? These are the formulas for x and y. So we'd have to eliminate t somehow, right? So the easiest way to eliminate t here is going to be to raise both sides to the 2/3 power, right? To get cosine and sine squared, right? So take both sides of this parameterization in both coordinates to the 2/3 power, right? To cancel the 3 and raise it to a 2. So now you could, what does this imply? Together, you could add those equations, right? So you get x to the 2/3 plus y to the 2/3 equals 1, because cosine squared plus sine squared equals 1, right? So this is a Cartesian equation for that same path. Right? This would be a Cartesian equation that would define that path. Which is kind of cool, right? Because it looks a lot like the unit circle. The regular unit circle, right, is x squared plus y squared equals 1. This is x to the 2/3 plus y to the 2/3 equals 1, which makes sense because we cubed our parameterization. So you need the cubed root of the x and y coordinates to give the same points, right? So now here, what could you do? You could then take this and um, solve it for y, right? So you'd get y equals, 1 minus x to the 2/3 raised to the 3/2, right? So now maybe you could use the Cartesian arc length formula, right? And well, this has a plus or minus, but at least on at least that first quadrant, right? So you could try this. You could try saying, okay, this is call this your function f, pick just that top little arc there. Call that your function f, and then do so 1 minus x to the 2/3 to the 3/2. And then you could integrate, the square root of 1 plus f prime of x squared, right? That's the sort of the Cartesian arc length equation, right? You could integrate that as x goes from 0 to 1. And I think this would end up being like a super awful trigonometric substitution, right? I think you need to let x be tangent cubed, or sorry, sine cubed. I think is the sine cubed of theta. Right, that would be the trigonometric substitution for this expression. Which at that point, notice what you're doing here. What is this trig sub? It's essentially this parameterization. Right? It's just calling x the sine cubed instead of the the y, the sine cubed, but it's essentially the same change of variables, right? So this is what's funny here is the if you try to say, well, can I just solve this with x's and y's? Yeah, you can kind of, but the only way that you would, and maybe you could push this through and maybe it's not that bad, but still, pushing it through, even the only way you would push it through, the standard method of integration just puts you right back to this parameterization. So this parametric description of the curve is really the right way to go. So, all right.